Okay, thank you everybody for joining a session on using Unity as an engine for real-time 3D in industry and in infrastructural projects. We have built a solution upon that called Perspective. We is me, myself, Guido van Gagedonk, and my colleague Peter Waterings. Our team is larger, but we are the ones presenting the solution. Peter will join me during the Q&A, and I will do the presentation. And I will try to dive in. We are Unit 040, and we have built Perspective upon Unity to give you the power to build digital twins. Why would you do this? Why would you want such a thing? Our vision is that it helps you to do things less wasteful than we do at the moment now. Build fewer prototypes, utilize technology and information you already have in your assets, and use engine technology to show what things are going to do. So to do it less with less resources and less wasteful than we are doing now in industry and in AEC. This is driven by a question from industry. Our solution has been built by a need from Canon to build machines quicker than they did in the past and to do them more effectively. They were looking into ways to do more digitalized versions of those and use agile processes for that, combining the three main data types we have in industry at the moment. So that's CAD data, that's kinematics, physics, and logic. And just to give you a glimpse of what we can do with that is a small teaser of the product and also the possibilities you can have within Unity yourself.
In an ever-advancing world, digital technology now allows us to realize a fully working digital version of a machine, a digital twin. Meet Perspective, the first digital twin platform at the forefront of this disruptive development. Perspective enables you to develop and test your machine in the virtual world before the real machine exists. The platform is so interactive that it behaves exactly as the real machine would. Even the same control software runs on both digital twin and real machine. Unit 040 is a company with years of experience and recognition in smart visualization for the high-tech industry. Come and see the future in Perspective.
So what do I mean with the digital twin? Because it's a hot debate on definitions for digital twins. But we mainly focus on building virtual prototypes for virtual commissioning, which you can then later use as an IoT data container. And this helps you to, for example, do testing, to virtual damage testing, look at predictions and see what happens on the machine. Here you see such a use case. This is for a Nordsonic company that builds semiconductor plants and products. And they utilize the technology to build the product on the right in the virtual world before they start building the actual one. And you can, of course, say, but we already do this in CAD tooling files. But with Unity and a real and discrete engine technology, you now have the possibility to build discrete, real-time virtualizations and simulations of your world. So that is what we are working towards. We discretize the CAD models, but we also inject physics and logic so that you can utilize the best of both worlds. And this is also, of course, a thing that can help with getting communication. If you now look at how machines are being built, there is probably a team in engineering drawing designs in CAD of a system. There are people working and figuring out where to put the actuators and the sensors and which ones to buy and which ones to connect to electronics. And there are teams building the software for the system. And of course, you have the whole, so people using the system. Now you have an ability to hook that all up one level higher into a fully working virtual prototype in which you can have discussions on. So you can even bridge the communication gap you might have had with your colleagues. We do not fully glimpse and understand what you are doing for programming, for example. And you can start earlier. One of the biggest needs and the questions we got from engineers on the software side, give me something I can program on. So give me virtual geometry in which I can already try to test, build software. If you look at companies that have to build machines quicker and better, this is one way to make the lead time shorter of the development of such a system. So what are common use cases for digital twins? There are more than just virtual prototyping. You can, of course, also look to throughput optimization if you have built a virtual version of your machine. And one talked a lot about is predictive maintenance. And then I mean really predictive maintenance, not analytical maintenance. Those are possibilities you get when you connect IoT data, for example, also to real-time 3D. So then you can hook up real-time simulation to your IoT stack. And the new one coming online, or not new, is machine learning on that all. So not only on the programmer of the system, but also on the geometry of the system and on the finitude of the system, so the logic, the sensors and actuators of the system. Your algorithm can help you. It's, of course, an extension of engineers to look into better constellations of a full system. And, of course, we can also train humans on such a system with training tooling, enlarging and extending this virtual container. So what goes for industry, of course, also can go for construction. If you're building a bridge or a tunnel, you don't have the possibility to build a prototype. You want to do as much as possible virtually. Of course, you can rent a large hangar and hang some turbines in there, but how to build a full thing when it's 3 kilometers long? You only have one shot of that. So this kind of tooling can help you to do better decisions on that as well. And the same goes also, of course, for aerospace, building complex planes, but also helicopters, combining all kinds of different stuff. And Unity is then a framework in which you can hook up already existing tools like CAD tools, but also CAM tools, CAE tools, and have one container really representing the full product. So this is a glimpse on, I will show you some use cases of actual clients which use the technology, how that looks like. This is the Unity editor you all hopefully love and work with. And it extends the editor extensions. So it brings better kinematics, kinetics to the system on industry standards, so with better precision, which is in gaming sometimes less relevant. Here it's very relevant. And it's being possible to hook that up to logic from outside, so to PLCs, but also software from the outside world or an IoT stack, and bridging the time domain, because that's another time domain than Unity normally offers. But to help people in industry, of course, we don't want to say throw away every tool you already use. We just say hook up the tool you already use. So inject your CAD model, sometimes utilizing Pixies or other tooling, and extend that by bringing back the kinematic layout, but also hooking up, for example, MDA tooling. So MATLAB, Wolfram, tools in which you can already set up algorithms for your total system. And hook that up to PLCs, logic controllers or IoT, so that you inject also and infuse the behavior of the system. And we leave that at the domain they're already working in, because then you validate what you are building, and you don't build a simulation to test your assumption. You just have a counterpart to test your software on, for example. You don't have to rebuild your software in a simulation tool. You have your software, you hook it up to a simulation tool. And if you then do that in full force, then you have the ability to build a virtual environment and a digital twin of your actual system. And then it can become even more interesting. You can start learning. So then you can put the system in the field, you start collecting data, and you can learn from the data you get and transfer the knowledge back to the systems in the field. And then you close the feedback loop. Because if you don't close the feedback loop, you will create a simulation, which can be a very faulty reflection of the real world. But if you close a loop, your simulation learns and your real machine learns, and that comes in full circle. That opens even the possibility for evolutionary design, so that you use ML in adjunction to what you already do with your own brain, to do steps, evolutionary, and spawn multiple versions of your machine and check the best ones, and then spawn that again. So really also, from a gaming perspective, spawning it again. So that really works. We try to make that as simple as possible. So upload a CAD file, and then define components within a CAD file. I will even suggest you some ways you can surpass this step. There are now things coming online, standards coming online, which already wrap this for you. Then you put in logic. You connect it to outside data sources. And of course, we built this to test things, not just for the sake of it. You build to validate certain assumptions you have of your system versus the world model, or on colleagues. Test, is this what we are going to build to your client? Is this what you want to have for an operator? Is it something you can operate? So you test also scenarios in this virtual environment. So upload, define, so this data prep, and then connect to data and start testing and validation your information. Yeah, I was already afraid for this. This directly also relates to tools, so it's called Perspective. It has editor functions, which you see here. They are Precisor, Prepare, the tools that directly help you to do the data setup within Unity, also extending the editor capabilities there. We have done this quite some time. We have built about 50 of those virtual and digital twins, and this is what our customers tell us. So we supply them now also the tools that they do themselves, but this is what they tell us. The reduction in the total cost of ownership of such a system can be 25% already, utilizing the normal data stacks they have built. They don't have to do something really new with their data. So what we mainly built is an interface model. An interface model utilizing Unity as cornerstone and bringing in data that's already available. So on the CAD side, but also on the data and software side. Also, for example, on the PLC level, but also on the IoT level. And also hooking in physics. One very interesting one for that is called FMU FMI, which is Functional Mockup Unit and Functional Mockup Interface, which I will show you later on. And that's one standard which Saab, Daimler, and Boeing are pushing also to industry because it helps with the next step of combining the data types, geometry, kinematics, kinetics, and the API of the interface with the system. So some examples of clients, one being Toyota. This is probably a device you have seen traveling here. They deliver the most of this kind of systems in the world. They utilize the technology to build full virtual versions of their system before they put them in the field, and also use them as a data IoT container to collect data on. So how does this work? Here you see the build version. So of course, if you want to see more, we have a booth 12, where you can see actual live demos. You can see under the hood what's happening in Unity. I will start up the clip. So this is one simulation running 11 modules, which have their own logic controller. So 11 logic controllers communicating to one simulated object. It does kinetics, kinematics. So there are trays moving over lines. They have some friction on that, and they are communicating directly to the PLCs. Of course, you can have level of detail, so you can, of course, put off the hood and look underneath it. So only seeing the logic of the system, for example, sensors and actuators. You can see very neat stuff. You can do visual debugging. You can see what your sensors are seeing in the field. And you can, of course, try all kinds of scenarios, throw away some trays, put in extra elements. And it gives you the possibility to also insert HMI. So we utilize the possibility to also feedback the HMI of the system into Unity, putting it back to the PLC, and the PLC runs the simulation. And of course, extending things from Unity using Mars or other VR setups and AR setups, you can be in VR in this environment. So you yourself can throw away, for example, a tray, or you can put off the machine and look what will happen, or try to totally mesh with the entire system. So, for example, trying to fool some sensors, putting your hand in front of it. Here you see also the visual debugging. You see that some lines, for example, are being crossed. And the interesting thing here is that you can also choose what you would like to simulate. You can do software in the loop, model in the loop, or hardware in the loop, and even a mixture of those. So that's exactly what they did here. Here you see the stack. This is one stack driven by MDA tooling, model-driven engineering tooling. And the other one is a hardware in the loop set. Here you see also the hardware driving this machine, just laying on table, communicating directly to Unity or to the simulation environment. So what we mainly build is a bridging object, which helps you to bridge those time domains. So to get the data from the different PLCs into this virtual world and back, because you build some logic in the simulation side as well. Where are your actuators, where are your sensors, and what are they pushing back to your PLCs, for example. You also see dedicated embedded controllers. So here they also have an X-ray, they have them virtually, but also on the table, which can do X-ray commands to the system. So we mainly focus on a communication stack that can also help you build your own layer on top of Unity to do this. And of course, being Unity, you can also add and spawn characters. So it brings you with powerful tools that you can also bring the people using the system in this as sprites or avatars, but also in VR. And even a combination of both, and then record what will happen. So you can also look at throughput. Can I manage and can I handle this amount of passengers in my system, for example? Other companies utilizing this, which I unfortunately cannot show you full live images, is Philips. They utilize this for the CT scanners to really set up and look at new designs for CT scanners, but also to look for real-time collision detection on CT scanners when they're in the field, and, for example, of course, to train people on. So then you get full circle with your digital twin. It travels over a line. You, of course, have to manage that also on the PLM side, and you try to get as much out of your data as possible, utilizing the next step in that real-time 3D. So this even helps them to do very precise spine pictures, which can be different per patient. For this, the system has to calculate on a real-time level the best trajectory. For this, it uses real-time 3D systems to do this as well, so that it even becomes a part of the solution which is in the field, not only a twin, but part as a real-time 3D object in the total system there. Of course, it also goes into manufacturing, so in plants. It can be used, for example, on a more conceptual way, that you have your building blocks of your plant, so you have your geometry with some logic, with logic controllers, or with maybe even some code, which can be, of course, also in Unity, and then you can think with it. It really becomes a kind of technical Legos in the virtual environment. And then you can start and build a plant layout. But, of course, also having the kinematic restraints. So there is, for example, a robot here, and then an engineer can check, can I manage these rotations? Can I reach the objects I would need to reach, for example, to transport my product over a line? Of course, utilizing PhysX, Havok, and even surpassing those, if it's necessary, on a higher level of detail for simulation. So also for point precisions in robots, for example, which industry needs for certain precision types. What goes for industry also can go for infrastructural projects. This is an actual bridge which has this virtual counterpart. That counterpart has an add-on Unity extension for real-time 3D. And that extension can be used to test the logic on. So they can, for example, test logic running from different PLC vendors to the simulation, and you push new software, you check against certain scenarios, is my software correct? But it is also used to train the operators on and to test very wild scenarios. You can, of course, also imagine new kind of scenarios which are hard to test in the field at the moment. And it is being then used afterwards and still as an IoT container. We do not contain the IoT data. The IoT data is in an own proprietary library or database, which can be some from Microsoft, AWS, but we can hook up to that. So then you can play what the actual bridge is doing on your visual simulation. That extends your normal dashboard of dials, which gives you maybe some information from your IoT data. This gives you also the visualization of the exact states of the system, so that you also richly see what's happening with your system in the field. And of course, what goes for a bridge goes as well for tunnels. Clients of us use this to do also very large geometries. So this is a tunnel, for example, of 3.5 kilometers of geometry with a lot of systems in it, a lot of turbines, a lot of lights, which are all managed, and traffic, for example, which can be managed in this. Unfortunately, I cannot show you the full clip of this. But if you want to know more information, please reach out to us on how to build up such a full, large system as well. Because it can scale to certain degrees and different degrees. So then, what's underneath? First, I said data prep. So we utilize most of the times also Pixies, for example, to get in the data. But we extend Pixies a bit more in the editor, so that you can do, for example, scrubbling within the geometry. So it can find the same kind of type of geometry. For example, a screw. You have to downsize this object a bit, maybe pushing it to the HoloLens or to another VR device. And then you can find all the screws and put them, for example, away, or you hit them in a kind of architecture tree. And it can help you to also bind certain parts of the geometry and rebuild the hierarchy in the geometry, for example. That tool is called Precisor, part of Perspective, to help you to utilize what you already get, for example, with Pixies, somewhat to a higher level even. And then it, of course, has to be set up as a kinematic layout. So it is breathing life into that CAD model, we have an own kinetic system in which can, for example, the restraints can be built in of such a system in the editor. We see that clients mainly use this in editor mode, so that they can always see what elements are doing in inspector view, for example. Of course, you can create a build, then you give it to somebody else, but here you can also manipulate the thing while it's in motion. You also see on the left that there are UI elements telling you, for example, what you constrained. So how parent and child relations in your kinematic layout are relating to each other. And even, of course, that's the next step, where logic elements are. So where is a motor, and what's on the motor, and where is a sensor. And you see, of course, here a sensor, so you also can see what the sensor does. And then, of course, you can utilize, so you can also mix different kind of physics elements. So you can use PhysX simply for from friction here. And then you combine the both possibilities to really build rich virtual prototypes. And the next step, of course, is to hook that up to logic behavior. In this case, the TwinCAD ADS direct link between this gantry and the logic, which is being written by a programmer, for example. And it maps, of course, the variable lists on each other, so it can send information both ways. So it's real-time, also data transfer in that. That's, of course, something we manage, so that is correctly done, and also that crosses the time domain of Unity. Other things, of course, robotics. So this is really kind of combination. This is crane/robot. So our tools also had to help you to more easily group your mesh, for example, and then rebuild the kinematic layout of that mesh. So to set restraints, to set wheel joints of this system so that the robot will act as your actual system will act in the real world. So here you see some tooling. So this is really tool sets within Unity to enable this on a more precise level than the editor itself can now provide. And then you can hook that up again to logic. So when you have built up your kinematic layout for this robot, you hook that up to a motor, for example, with some motor logic, so a start and an acceleration and deceleration graph, for example. And then it starts to behave when you push this start. So you can even, of course, do some testing within the Unity editor without using logic from outside. That helps you, for example, to do a unit test on this crane. Is it working as supposed to? And here you see how that works. You also see, of course, on the left back, some UI elements telling you how the things in the crane are relating to the geometry. So it's really mapping geometry on logic and then making it vice versa. And here you have, for example, two robots. So one robot is being rebuilt by a kinematic controller and kinematic layout. That's the right one. But the left one is directly injected. It's done by using a standard called FMU, Functional Mockup Unit, Functional Mockup Interface. This is kind of a zip file which you can directly inject. We have built an import for Unity into Unity. And this combines your geometry data with your kinematic layout and your API. So then you don't have to rebuild the model. And this kind of models can be, for example, built in Wolfram and System Modeler directly be injected. No conversion needed. It also gives you more performance. So then you can also trim down some of the algorithms in the robot. And it gives you a possibility to work with different suppliers. You say, make this container, then I can do a unit test on it in simulation, and I can combine things. And of course, one which I already talked about as a use case is collision detection. We bring you tools for more precision, Octree kind of tools to check collision types within Unity, not within Unity, but outside of Unity, but utilizing Unity, to also tell you if things are colliding, for example, on a high precision, if you are using these tools for robotics and handling stuff which need very high precision, endpoint precision kind of objects. And we bring you tools to, in more the conceptual phase, build up a spline system. So then you utilize Unity more on an animation scale type, and then we bring in spline and tensor systems that can go up clock speed, so even higher than the Unity engine itself does. It can do intertick calculations, and this is, for example, very handy if you are building AGV fleets and you want to test certain scenarios. Then you can also push the timescale up, so that you can use this in an ML training ground, machine learning training ground, for a certain part of your algorithm, and you set it to set, for example, dynamic tensors, And the paths are then dynamically adjustable in the editor when it's just in play mode. And then you can also scale the time up. So you can go to higher time scales. You adjust the time scale on the right, and the time scale goes up without dropping. We don't drop frames. This is linear calculation. So you can have visual frame drop, but not collider frame drop. So the things are more accurate in that respect. And it becomes very interesting if you combine this all. More of our clients are now looking into building fully autonomous plants. And of course, then programming becomes a real nightmare, for example. How do you program an AGV fleet of all kinds of robots going through each other? You have to do ML training for that as well. So then it really helps you if you have a virtual counterpart of what you're trying to build. This is what they call Industry 4.0. They are trying to build a plant which produces products uniquely, still with margin. These are smaller plants maybe that can really be dynamically producing toothbrushes or other stuff. And this is being then used as a training ground for the machine learning algorithms, for example. So then you combine all. So then you combine the fact that you have a logic controller communicating with such a plant, you have built a virtual prototype of such a plant, and then you infuse that with the capabilities of ML. And of course, Unity has a nice stack to put on the ML stack as well to this kind of plant types. And then not only on the behavior of the plant, but also on the layout. Can I do a different layout which is maybe better for my solution? And also looking at, should I put, for example, other objects in? And what is my throughput? Can I optimize my throughput and how? And to go full circle, because of course, I was talking about digital twins, you then directly can also hook that up to your actual objects. You can split the information stream. You have a virtual one on the left, and you have the actual one on the right, functioning as well. And then you can do one more thing. You can use your virtual one to, for example, play 1 hour ahead. You can look, can I do my batch production, which I have in a recipe here, on my phenotypy of my plant, yes or no? If no, that's a deadlock, then maybe I have to change something and rerun my simulation or my digital factory here so that I can do what I would like to do. Of course, we don't do this for ourselves. This is hopefully a solution that can help people and helps people in the field already, ranging from system engineers and system architects, which, because of the silos we now have in engineering, are sometimes completely lost. They cannot grasp the entire system anymore. This gives them a way to have visualization and simulation again, so that they see the full system working, so that they really can interact with the system. Software engineers, that they can be early at the party, so that they don't have to wait for, let's say, 6 months before the CAD engineering drawings are ready, and when there is maybe a prototype there to start programming on. Of course, it is not a silver bullet, it's an approximation, but at least gives you more insight than having nothing. So in steps, you see that people then start to work up that virtual digital twin, creating a feedback loop, even with a prototype, because sometimes you do not know what you put in your simulation, but building a prototype even helps you to build a better simulation, and then you can work agile. So you can, for the first time maybe now, create an agile approach to hardware development. You can create virtual steel, utilizing the same that we already love in software, do iterations more often than you can do now. For infrastructure, you cannot build real prototypes. In industry, maybe you can, but this can save on prototypes, and they can become even better than you already have. And I think it's quite clear to say that already helps also with marketing sales. For example, the example you saw in the beginning of the semiconductor products, it was pre-sold to the end customer based upon the simulation. Even the factory acceptance test was pre-done on the simulation while the machine was still on the boat. Of course, when hooking up, you do a final check, but calibration is easier. So downtime and uptime are higher. You are quicker with upspeed of your system than if you don't have this. And of course, we are all doing this for the client of a system, being it somebody riding over a bridge or using a machine or trying to produce microchips. It's a way to do it with less effort, with lower total cost of ownership, and showing and bringing them the thing they actually wanted. It's also trying to make things explicit which are implicit at the moment. So what do you need to build a digital twin? So you need things to do data prep. You need things to build up kinematic relations, to build better physics, to hook it up to logic, and to add actors like ourselves working with a system. And then test your assumptions, communicate about your assumptions. So these are typical some editor extension functions we add to Unity to utilize the strength of real-time 3D, fusing it with linear simulation to build virtual prototypes and digital twins. Of course, companies already are working on the lower levels. Now you get the possibility to go one level higher. You don't have to throw away all your tooling you already have. You just have a way like Pyramid of Maslow to go one level higher, combining the data sets and bringing the strength of gaming engine technology to industry. So what we're seeing now is that adoption is quite fast. More and more companies, of course, are on the brake. They have to do something different. Things have to be done better and more efficient and less wasteful. These are tools for agile development that help them. And it opens the way for continuous model-based development. With that I mean that even when a machine is in the field, going back to the case of Philips, for example, you can more easily insert new code. One of the cases there, for example, is if you now want to put a new code for a CT scanner, you have to go through the FDA approval rating system all again, trying it on an actual system. This system can help you to do this virtually and quicker, even for all the different machines you have in the field. And it then opens the way for evolutionary design on all the three levels. On the hierarchy, on the CAD model, on the phenotypy of the system, so where are my actuators and sensors, and on the behavior of the system. That is briefly an introduction in how you can utilize real-time 3D within Unity, extending it and hooking it up to data sources in the field. I hope that you found it interesting. And I think we have quite some time for questions. And that's also why Peter joins me, because I do not do that much production code anymore. So he has to do the fill in my blanks where I cannot answer your questions. So thank you for your attention, first of all. Are there questions? If you have a question, you have to walk to a mic, but most of you have probably already seen this.
So, hi.
Yeah.
Thanks a lot for the nice presentation. First question is, you talked about the PLC.
Yeah.
So, how's the benchmark or how's the test when you are talking about the connection of the Unity with the PLC? Like how it's going on? The latency is too high. Either it's going via some Python libraries, S7, or via OPC. How?
Maybe you can answer that directly, Peter. It's already on. If I'm
okay, so yeah, you can hear me. So right now we offer a direct connection for back of TwinCAD ADS. So that's for the virtual PLCs or soft PLCs and actual PLCs. We offer a connection for Siemens F7 and OPC UA. I guess, does that answer your question? Also, I guess maybe I should name that for more high-level control, you can also use ActiveMQ or MQTT to directly connect with the actuators and sensors within the simulation.
Yeah, we mainly build a messaging bus. Maybe that also answers your question, which bits the time domain gap. So the millisecond delays which you can have that Unity cannot respond, it figures out and it gives you a message back or not.
Is there anything done with Simit also?
Sorry, no connection to Simit just yet, but we're developing that at this time.
Okay, thank you.
Thank you.
Another one? No, we don't see. We cannot see, so... No more questions? It cannot be all that clear already. Nobody want to challenge this? Seriously? Okay. Thank you for your time then, if that's all.
Thank you very much.